Hello everyone, we will discuss a problem called minimum meeting rooms. This problem states that given a list of intervals, with each interval representing the start and end time of a meeting, we need to find the minimum number of rooms required to hold all the meetings. So let's look at a couple of examples to understand the problem statement. So here we have a list of meetings, 3 meetings in this list, each with a start and end time. And we would need to return how many rooms would be needed to hold all these meetings at a minimum. So let's look at the problem. So clearly there is an overlap between the first meeting and the second meeting. So we will need 2 rooms for these 2 meetings. If we look at the third meeting, the start time is clearly after the end time of the first meeting. So when the first meeting is over, the third meeting can be held in that room, so we need 2 rooms. Let's look at a second example. So in this case, we clearly have an overlap between the second and third meetings, and we have an overlap between the first and fourth meeting. However, there is no overlap between the second and fourth, and there is no overlap between the first and the third. So we can make do with 2 meeting rooms, one where the second and fourth meeting will be held, and another where the first and third meeting will be held. So the answer is 2. Okay. So this problem broadly falls under the merge intervals type of problem. It could also possibly be categorized as an arrays problem. So we discussed the solution. So let's think about this one more time. So the first thing we would have to do is sort the input list of meetings by the start time. So in the first example, we already have that sorted. So our algorithm will be something like this. So we have a first meeting, then we have a second meeting which clearly overlaps with the first meeting, and then we have a third meeting where the start time is greater than the end time of the first meeting. So our algorithm will have to keep track of the end time of the meeting, and if it's less than that of the start time of the meeting we're looking at, then we can hold that particular meeting in the same room where that other meeting was being held. So we need some kind of data structure to keep track of the end times. Okay, let's look at the second example. In the second example, I already went ahead and typed this out, where we have sorted by the start time. So clearly first and second items here overlap. Now if we look at the third item, so the third item, the start time is not less than the end time of the first meeting, so this meeting can be held in the room where this meeting was going on. Moving on to the final meeting. So once again, the start time is not less than the end time of the next meeting in the list, so this meeting can be held in the same room where this meeting was going on. So basically we need some sort of data structure to keep track of end times of previous meetings. Obviously we also need find overlaps. So I think these are the two key points. So okay, so I have pad up here. So let's see if we can write some code. Okay. So I went ahead and typed out the examples here, and I created this stub method where we're going to write some code. So we have the meeting object here with the start and end. We have the constructor where we can pass the start and end. Okay. So as I had mentioned, the first thing we got to do is sort the input list of meetings. So we have to sort by the start time. Okay. And then we obviously need to return the minute, right? So let's initialize this to 0. Now we need some kind of data structure. I think priority queue is the data structure we can use here. Okay. And we need to pass in a comparator as well. And the comparator, right, so the comparator has to be the end time here. Okay. We need to walk through the list here to make that check. To make that check, we discussed where we look at the start time of the current meeting and see if it's less than the end time of the previous meeting in the queue. So actually, so let's think about this for a second. So the way we would have to do it is so if the start of the current meeting is not less than then we can use that meeting in that other room. So how do we do this? So so we would have to, oh right, because we not just compare with the last one, but we have to compare with everything that's previously in the queue. Okay, so I think we would have to use a while loop here. Right, there's a typo. Okay, so we do a check queue is not empty. Let me do a quick. I'm gonna disable put. I'm gonna keep the brackets, but I'm gonna disable the auto completion because that's good for practice. Okay, so while it's not empty, and then the check we have right when meeting the start is not less than, with me has a greater than equal to. Okay, so we have to check. We have to. I mean, we can do a peek. Dot. Okay, now I'm wishing I hadn't disabled the autocomplete, but anyway, let's see how dot n if it's right. And that's the check we need to do. What am I missing? Right, as long as it's, so we can use that same other room, so we just, right, so we can use this, okay, so we can use the queue as kind of a record keeper for all the meetings we care about, or all the active meetings, so to speak. So queue, I think it's full. Okay, so we remove that, and then we add this this meeting. I don't think it's in. I think it's offer, if I remember correctly. Okay, and then right, and then we're using the queue. Okay, what's wrong here? Okay, and then we're using the queue as our record keeper for all the active meetings. So we can use the size, right? So basically, we can use the size of the queue. I think we have to use the max here. Min rooms, and then queue dot size. Right, and then finally return min rooms. I think that should be it. Okay, that was it. Let's think about it for a second. Let's add some comments here. So this is the critical check for reusing room, and then the meetings, right? Okay, let's think about edge cases. Well, okay, yeah, we have to like the if meetings null or it's let's run this again. Okay, everything's good. Okay, that was it. So let's think about time complexity of this code. So obviously we're doing a sorting, and sorting takes, it's n and log n. Now we're doing some operations with the priority queue, we're doing peak and poll. Now peak and poll, I believe that takes of log n, so overall time complexity would be O of n log n. So space complexity is, I think it should be obvious, it's O of n. The worst case space complexity is O of n. And of course sorting space complexity also takes O of n, so time complexity of n log n and space complexity O of n. Okay, that was it. Thank you for watching. Bye.